In this lecture, we'll discuss another minimum spanning tree algorithm, that is the Prim's algorithm. The idea of this algorithm is very simple. The idea is that we start from an arbitrary vertex, that is maybe V1. It is connected to several other vertices. What we do is that we actually try to start from this vertex V1, and then we actually adjust the distances of all the adjacent vertices, and the distance would be the cost of this edge to the respective vertex. So we adjust the or update the vertex, the distance of all the vertices that are adjacent to V1, and then the next step would be that we would pick the vertex that is the closest to V1. So in that way, what we have is that this blue edge, that is E1, it is of the smallest cost. So we picked that edge, and we used that edge in the minimal spanning tree. So using this logic, now we show that if we want to connect this V1 with the entire graph, this E1 is the smallest edge that can connect this V1 with the remaining vertices. So this choice of picking E1 as an edge in the minimum spanning tree is the correct choice here. Okay, now after this minimum spanning tree algorithm actually takes a greedy choice. Actually, we have a complete domain of algorithms that are called greedy algorithms. So this minimum spanning tree algorithm, the Prim's algorithm, it is also a greedy algorithm. And what it does it is that after concluding the processing of V1, what it would do is that instead of going to any other vertex, it would just try to pick the vertex which has the smallest cost. So that is V2 in this case. So from V1, we would move to V2 and keep going the spanning tree to reach the entire graph. So that's the entire idea of the algorithm. Let's see the pseudocode, and then we'll go through an example as well. So um, the overall the algorithm, the condition on which the algorithm would stop is that it would pick n minus one edges to connect the n vertices of the graph. And another angle to see this algorithm is that this algorithm is actually a depth first search algorithm. Okay, so what we do is that when we start with one vertex, we actually update the costs of all the adjacent neighbors, but then we would go to one vertex and explore from that vertex onward. So that's a depth first search algorithm as well. So the overall algorithm is that we'll actually see an example as well that would be easier to understand, but let me give you some overview that how we go about this algorithm. So for this algorithm, the input is a graph, that is W is a weighted matrix of the graph, and this R is the starting point from where we would start growing the minimum spanning tree. So the first step is to insert all the vertices in the graph into a minimum or priority queue. Okay, so this queue is a heap. This is a minimum priority queue. So after that, what we do is that at this point, we have not set any key of these vertices in the queue. So the first step is that we would just, in these two lines, we would just update the key of each vertex as infinity. That is a bigger value that we would not expect to be the cost of any vertex. Okay, the cost of the vertex would be the cost of reaching that vertex via an edge. So initially we would say that we do not know that which edge would be appropriate to reach a vertex. So all the distances of the vertices from this source vertex R would be infinity. Okay, including this node R. Okay, then we update the cost of this R, that is the starting point, this R vertex to be the 0. That's the minimum value that it can have. So in a minimum priority queue, if we set or update a key, uh, even if it's below in the tree, it just percolates up or heapify up to the root. So this would become the root of the or the first element of the queue. Okay, the heap is actually is a tree, so the minimum value would become the root of that tree. Okay, then what we have is we have another array, that is the p. It's the array in which we save the pointers or the some references of the parents of different vertices. So a parent of a vertex is a vertex from which we traversed on an edge to reach this specific vertex. Okay, so a vertex before reaching this current vertex is the parent of the current vertex. So we would save those parents in this array P. And what we have done here is that we have set the parent of this node R as null. That is, this is the starting point, and we have not yet discovered any other vertex. And this vertex R has no parent because we have started from this parent, from this node. Okay. Then what we would do is that after setting this parent to null and the key of the first element as 0, we simply go into this loop. And what we do in this loop is that while queue is not empty, we know all the edges, all the vertices are in the queue. We extract the vertex that has the minimum key, and that is definitely the R node here, the first node here. We extracted the first node, and for the first node, what we have done is that all the nodes adjacent to you, this is the notation of seeing that U has an adjacency matrix. So in that specific row of the U matrix, of the adjacency of the adjacency matrix of U, um, we go to all the connected nodes and call them V. And for each V, what we do is that if this V is still in the queue, the same queue, if it's still in the same queue, that is, it is not processed yet. And the current weight between U and V, U is our starting point and V is the neighbor. So distance between U and V, if it is less than the already discovered distance of node V. Remember, we set the key of all the vertices except for this starting vertex as infinity. So for the first node or the root node, what we have is that we would have the key of all the adjacent nodes equal to infinity. Okay, so for infinity, this condition would always be true. So we would update, because all the nodes are not processed and the weights of all the adjacent nodes of node R are infinity. So we would update the weights here in the second line, and in the first line we would set that the adjacent node V, uh, we would actually set the parent of that adjacent node as U. So U becomes the parent of all its adjacent nodes. And then we set the or update the key of the adjacent nodes to be the cost of the edge between U and V. Remember, this W is the weighted matrix, and the entry in this W matrix at the positions UV is the cost of the edge between U and V. So we use this cost to update the array that we call the key of the specific vertex. So in that case, what we would have is that the same scenario, this maybe is the R node, and it has maybe 3 different connected vertices. And initially the cost of all these vertices were infinity, and the cost of this node R was 0. But what we have done is that we have processed each node one by one, call these nodes as V, and the cost of this is the key of node V. So we have compared this key of node V with the cost of this edge, maybe E of V. So definitely this cost of edge is less than infinity. So we would update this as EV1 maybe. This is EV2 maybe. If this is the second node, then EV3 would be the new key of this vertex. Okay, so we'll use this algorithm, we'll keep doing this, because after this for loop, for loop for the adjacent vertices, we have removed this R from the queue. And when we would go back into this into the iteration of this while loop, when we would extract another element from this queue, we would actually pick the vertex which has the lowest key value here. Maybe if v1 is the lowest key, so we would keep growing the tree from this v1 vertex. Okay, and for that vertex we will again repeat this process to update the keys of the adjacent nodes. So that's the entire algorithm. Let's run this algorithm on a sample graph. So this is the graph, and we have 1 2 3 6 and 2 8. We have 8 different vertices, and we have several edges between them, and these are the undirected. This is an undirected graph. So starting with this, maybe the R node initially in this for loop, we updated the keys of all the vertices and set these keys to be infinity. Then we set the key of the starting node. This is the starting node. We set this key as 0. Okay. So now this would be actually the root node in the heap. So, and we set the parent of this root node to be null, that is the starting point. It does not have a parent node, it's the head of the root of the tree, of the minimum spanning tree. Okay, then we go into this loop and we extract this vertex. So we colored it red to show that this node is now not in the queue. All the blue nodes are in the queue. So we extracted this node and we update the value of all the adjacent nodes. So this node u to adjacent these node are this one, and these two nodes are adjacent to this node u. So what we have done here is that we have updated the value of first node to be the cost of the edge, that is the 3, and we compared it with infinity and we set the value of this node to be 3. Similarly, for this node, we would update the key. We would compare this 14 with this infinity. 14 is less, so this condition is true, and we would update this 14, this infinity, and we would write 14 here. Okay, so this is the starting point. We have completed this for loop for this node u. This node u is not in the queue now, and the top of the queue, or the root of the heap, would be this node, this which has the smallest key here. All the remaining keys are infinity. The node on the upside has key 14, and the node below has the key 3. So this is the root node of the heap now. This is the minimum value. So now we extract this node from the queue, and the adjacent nodes are these two nodes. And for this specific node, the cost from this node 3 to this node is 8. So this cost of 8 is less than this infinity value, so we would update this value here. We would update the key of this node as 8, and you see from this node 3 we have this edge of cost 10 that can connect this node 14 with this 3. So instead of having this 14 edge to connect this node with the minimum spanning tree, we would use this smaller edge. Okay, so this 10 is less than 14, so we would update this 14 as well. So the cost of this node would be now 10. So we have actually updated our decision. That was the greedy choice to update this value to be 14. Then at a later stage, we found that our first choice was not correct. Instead, connecting this node 10 with this 3 with the cost of 10 is a better choice. Okay, now again, you see these black arrows, they are actually representing this array P. Actually, we have an array, and what we have done so far, maybe if this is the node number 0, it has no parent, so we set null here. And for this node number 3, we have this parent as node number 0. Okay, this is node number 3, maybe. Let's call, if I call them, if I just write these black nodes as here. And then for this node 8, for example, we have parent 3. This is for node 8. And for this node 10, we have parent as 3. So this is the array P that is also being updated here, but we have not shown it. Instead, we have shown these black directed edges to show that the parent of this node 10 is 3, and the parent of this node 8 is also node number 3. Okay, so now I'll I'll just pace up a bit because the algorithm is now clear. Uh, so among these two or the remaining blue nodes, the minimum cost is of this node 8. So we would extract this 8 from the queue. The adjacent nodes are these two which have infinity cost. So we would update the cost with the cost of the edges. So 15 would be here and 2 would come here. So that's the next update. And the parent of these two nodes is now 8. Now the minimum value is this 2. We extract this value from the queue, and the adjacent nodes are 1, 2, and 3. And this node is already processed, so it's not in the queue and it violates this condition. It does not satisfy this condition. That is why we would not process this node 8 again. Instead, what we would do is that we would only process these three blue nodes that are connected to node number 2. So this infinity would be updated with the value of this edge 9. This infinity would be updated with the value of this edge 4. And again, you see, this 10, this is not the correct cost to reach this vertex. Instead, uh, from this node 2, this edge 5 is a smaller edge. So we would update this 10 and we would update the value as 5 here. Okay, so we have updated all the three values again. Now, from these four blue nodes, these four blue nodes, the minimum value is this node number 4. So we would extract this node from the queue now, and the only unprocessed connected node with 4 is this one. All the other nodes, that is this node number 2, is processed, so we would not update its value. Instead, we would update the value of this. If it's updating, we would update the value of this node, or we would compare this previous cost of this vertex with the cost of this edge. So this 5 is already the smaller value, 6 is a bigger value, so we would not update this 5. It would stay there. So we have not updated this value. Now we extracted instead among the three nodes, this 5 node, this 9 and 15, the smallest value is 5. So we extracted that node from the queue. No connected or adjacent node is unprocessed, so we would not do anything for this node number 5. Then from these two nodes, 9 is the smaller value, we'll extract 9 from the queue. And it also has no unprocessed adjacent node, so we would not do anything for this node as well. And then the last node, that is the only node in the queue, is extracted, and it also does not update anything, and the algorithm terminates when the queue is empty. So after extracting this 15, now we have no more vertices in the queue. So that's where we actually stop this algorithm. This while loop terminates and the algorithm stops. And if you can see, starting from this node number 0, what we have is that we have now generated a spanning tree here. Okay, so if you want to see, if I just draw this tree here, this is the node number 0, and it is connected with node number 3, and this node number 3 is further connected with node number 8. Right now, this node number 8 is connected with two other nodes. So the two nodes are 8, 2 and 15. So this is 2 and this is 15. And then 15 is not connected to anything. This 2 further grows the tree, and 2 is connected to the remaining 3 nodes. These are 5, 4, and 9. So this is the minimum spanning tree to connect this specific graph into a spanning graph. Okay, now if you see here, if you just write the cost of these edges, you would see that these edges are the edges that have the least cost in the entire graph. We have actually not used the edges that are redundant here. So we have neglected this edge 10, this edge 6, this edge 14. And apart from these three edges, we require all the other edges to connect these 8 vertices. So we have picked 7 edges that are of the least cost. So the idea is same. We need to pick the edges which have the minimum cost and they connect the graph. and eliminate the redundancy in the graph. So that's it for the Prim's algorithm. There are a few. There's another example that you can follow. Instead, I would just go to some a comparison between Prim's and the Kruskal's algorithm. There are few points that are important to note here. Is that for a Prim's algorithm, the graph must be connected, because what we are doing is a depth first search for a Prim's algorithm. So a depth first search would only reach the vertices that are connected in the graph. It would not go to the unconnected portion of the graph. That is why this Prim's algorithm would not work for the disconnected graphs. Okay. Whereas Kruskal algorithm, it actually takes the adjacency matrix or adjacency list as input, and just pick the edges from that specific adjacency list. So it does not need the graph to be connected. Okay, Prim's algorithm is significantly faster for dense graph. It means that it does not need to sort anything beforehand. It just keep parsing the vertices. It just pick the edge that is of the smallest cost and ignore all the remaining edges. So this Prim's algorithm actually performs better when there are many edges between vertices. Whereas the Kruskal algorithm is a better algorithm when we have a few number of edges between the vertices, because sorting them would be less cumbersome. And then what we can do is that if we have those sorted edges, we can just pick n minus one best edges from those specific from that specific graph. So Kruskal algorithm works better when the graph is a sparse graph. Okay, so that's it for the minimum spanning trees. If you have any questions, you can ask in the next lecture.